Okay, we spoke about measuring model performance by a single number, right? Well, you can carefully construct a number in one way or another way such that it captures what you need to capture. But is it a good idea to, given how many unknowns and domain specific requirements are there, is it a good idea to use a single number for representation of all of that complexity? Well, generally not. Generally, it's better to demonstrate and show as much as we know about the problem, and a visual map of model performance would help then. And furthermore, even specialists would have hard time understanding your results if you only show them one number. A figure is worth 1,000 metric numbers, or is it? 1,000 measurements can make a good figure, right? What I mean here is that when you're talking to your stakeholders, they may be better convinced if you show them how your model performs in a picture rather than just a number or a bar plot of comparison of two numbers or so. So remember expected value calculation. We had something that came to us from the sales department, cost benefit information. Well, sales department, I'm kidding. We have to be very creative, as I said in the previous lecture, to actually compute this matrix or fill it with values. And benefits everywhere, just the negative ones, as you remember. And then we had this after we trained our classifier, our model, decision tree in this picture, in this case, we took a test set and computed the confusion matrix. True positives, false negatives. That's all we have, right? This process is deterministic, so the expected value is the result that we'll get. Where would the 1,000 numbers come from? Well, remember that Bayesian decision boundary? And this is a cartoon, but imagine we have patients with cancer denoted with the red curve here, and patients with without cancer denoted with the green curve on the left here. So decision boundary, optimal Bayesian decision boundary is right here where those curves or probability density functions, posteriors intersect, right? And then anything from the red that failed on this side will be predicted as negatives, as no cancer, and anything on the right here will be predicted as having cancer, or any patient on the right will be predicted as having cancer. So overall risk is minimized by having this decision boundary, Bayesian decision boundary. But false positives and false negatives are not equally costly or not equally expensive. We don't want to be false positives in generally, right? We don't want to predict a patient. Well, actually, in this case, in the cancer, we don't want false negatives. We don't want to say a cancer patient, a patient with cancer, that they don't have cancer, and let it go into stage 4. So we'd rather over test patients without cancer than let a patient with cancer die, right? So let's look at a slightly different picture of the same thing. So we have two probability distributions. One is for one class, another one is for the other. And this is healthy, no disease, just conveniently flipped so we can see those regions better. And disease. And this cutoff, the Bayesian optimal decision boundary, it's not anymore optimal, it's just a decision boundary. If our false negatives are less costly, then we can allow more of them, and false positives are more costly. We are moving a cutoff to the right, so we will have less of them. Okay, well, with respect to cancer, those figures don't fully align. We do want to move the cutoff further here because we are okay with not false negatives. We're okay with like we can't say we're not okay with false negatives. Sorry, we cannot say that the patient doesn't have cancer when they do as easily as we can say. And don't get me wrong, it's still an emotional stress for a person with cancer or a person without cancer who was told they have a cancer, but it's still worse not to notice a cancer and let the person go with it. So you see, everything is flexible. If we're in the Bayesian world and we have decision boundary, we can move it back and forth, change it as we wish, and every change, see, false positives are changing and false negatives are changing. So our confusion matrix is changing as we move the decision boundary back and forth. So this whole matrix will change. The numbers will be different. So depending on threshold, the numbers are changing and confusion matrix changes. And our cost, expected benefit with the cost-benefit matrix multiplication of the probabilities will also be different, not just depending on a different model, different hyperparameter settings, but also dependent on how we set that threshold. But not all of the models are actually probabilistic because, for example, support vector machine, remember, we had the decision boundary, we had our supports, and we could rank maybe our soft margin. We could rank our samples by the distance from the decision boundary. But this distance is not probability. Even if we normalize it to 1 by the furthest, to go from 0 to 1 by taking the largest distance and dividing all distance by it, still it's not probability. It's just a score of how close is the model or how representative the sample is of its class, I guess. But even when we're estimating a probability distribution, like in your naive Bayes homework example, where you were using kernel density estimators to arrive at the estimate of the probability. But even then, we may not be able to get sufficiently representative training samples, so those are not truly probabilities either. So what do we do in this case? So a classifier is equipped with a confusion matrix. Once we have a classifier and a test set, we can produce deterministically a confusion matrix. Here it is, right? When the threshold changes, the confusion matrix will change as well. And the numbers are true positives and false positive change, and as we discussed. So with our ranking classifier, a classifier plus a threshold produces a single confusion matrix. Note that not all classifiers return a score. Some of them are truly just 0-1 loss. But you, for most of them, you can generate a score, as like support vector machines say, it does not return a score, whereas logistic regression returns you a score that we're looking for. And if we're training a neural network and using softmax, we're also getting a score from 0 to 1. But don't confuse it with models probability, model assigning probability to the sample. It is confidence score. It's still a score or confidence value sometimes. So with the ranking classifier, classifying plus a threshold produces a single confusing matrix. So let's take all of our samples, all of those instances that we have, and those are your features, instance descriptions, right? I don't like green. Yeah, let's use purple. And each of them has true class. We know this is our test set, right? We know this is positive and this is negative. So for some model, let's call it classifier 1. Yeah, typo. Let's call it classifier 1. We run the features through the model and it returns our scores. We sort all of our test samples from highest to lowest score. And now we can choose a threshold in the score space. So for example, right here, this line, we set a threshold to 1. Let's just do 1. Oh, wait. No true positives, no false positives either. We predict everything as negative. 100% is predicted as negative, or 100 samples in this example, in the picture for convenience, right? They all are, well, there are 200 of them. They all are predicted as negative. There is, if you look at the truth, we have 100 negative samples in this test set and 100 positive samples in this test set. When our threshold is 1, everything is predicted negative. This is what's predicted, remember? This is what is actual. Then we set threshold to 0.98.5, slightly above the last sample, but the second to last sample. So only the last sample makes it. This last sample makes it through this threshold. That means the model assigns it to the responders class or to the positive class. And in this case, it happened to be true that the model is correct. It's assigned that one to the positive class, and it is in the positive class. So now it moved from false negatives to true positives. And we have 1 true positive and 99 false negatives. Let's lower our threshold. With the second example, the model happened to be correct as well. So we have 2 true positives and 98 false negatives. The true negatives don't change yet. But, oh, look, if we move lower, we start getting negative examples. So the model incorrectly assigned a high score to a sample that is really negative. But the high score means positive. So we are getting 2 true positives as before, but 1 false positive now. So our true negatives samples, number of true negative samples is changing, is lowering. And then we'll go further and further lowering our threshold, and we get changes in our confusion matrix. It is different with almost with every, it doesn't have to change, but it's different with every shift of threshold, the cutoff. So note, different classifiers produce different scoring of the same samples. That means this figure for classifier 1 has 1 order of true class and 1 order of corresponding instances features. But when we apply a different classifier and sort by its score, the number of samples is the same, but the order is now different. Get that? Okay. So the questions now, how do we compare different rankings? So we have few classifiers and few rankings. How do we compare which one is better? How do we choose a proper threshold? So the answer is profit curve. With a ranking classifier, we can produce a list of instances and their predicted scores ranked by decreasing score, and then measure the expected profit that would result from choosing each successive cutoff point in the list. Let's look at it. Let's assume, just to understand what a profit curve is, let's assume our profit margin is small, an example. So we're still in the marketing case. So, and our marketing material and sending our marketing material costs us $5, and each responder, so $5 to ship, and each responder pays $9. $9 responder. So in the end, each responder brings us $4. You probably want to pause the video and try to construct cost-benefit matrix yourself, but here it is for you. So we have true positive brings us $4, and false negative brings us false positive brings us negative $5. So we spent $5, but we spent $5, but we don't get anything back. We don't get our $9 that we hoped for. So for this example, this is our cost matrix, cost benefit matrix. And we're considering 3 classifiers, 1, 2, 3 here. And we're also considering a random classifier that randomly assigns the responder or not responder. Shall we send the package or not? So, or just randomly shuffles the order basically in this case. And the score, I guess, in a random classifier is linear. We notice that we all start at the same point. That's one thing to observe. Another thing is observing that if we put this line here, notice that profits can go negative. By working too far down the list and making offers to too many people who won't respond, we're spending too much on the cost of the offers, right? We just keep spending, but people are not responding, so we're not recovering our investment. And the curves begin and end at the same time. Well, when they begin, the threshold is 1, and everything is assigned to negative, right? No positives with this threshold. But the same happens at the end. Everything, notice, note one important thing. The test set is the same. And although this exercise may look for you academic, don't be fooled. This is very practical, very practical knowledge that you're gaining. This is important in deciding in production how to use your tools, your machine learning classifiers or regression models, such that your stakeholders are happy, your company is earning money and saving lives, right? So the end point is the threshold is 0. So everything is positive for all of the classifiers. Anything in between is different because the order of the ranking, according to the score of each model, is different. So what do we observe we observe that our maximum profit is here. It's somewhere above $200, maybe 250 or 240, I'm not sure. And it happens around 50% of our test population. So now we want to say, okay, look, I can overplot my score line, the confidence, or this column, and by that, on its axis, I can figure out what the threshold is. Now in production, I should use classifier 2 as the one that gives me maximum profit with this specific threshold. I could also guess that I will send, using this classifier and the confidence, I will probably be sending my package to half of the customers that I pass through my classifier. But that's okay, because I will still get on average profit from, I just want to be more than zero. That's already good. I'm making money. But imagine a situation when you have limited budget. It's not that, okay, well, just take max profit and keep sending stuff out for half of the customers. Imagine, or think about a situation when you have 100,000 customers, but only $40,000 for your marketing campaign. What shall we do? Well, profit curve can help us there as well. $40,000 with $5 per marketing brochure or marketing material gives us 8,000 customers that we can send the money or the offers to. So instead of sending them randomly, we can send them to top, which is this 8,000 out of 100,000 is 8%. So this line, at this line, if we observe, now classifier 1 is better. And we pick, if we're on a budget and only can send marketing material to 8%, then we should send it to then we should use classifier 1. So the important point about those curves, like what does it mean? Why are they jumping up back and forth? Why are they growing at different rate and then going down? Is that the models are not as accurate at every confidence intervals. So when they're showing, some of the models, when they show high confidence, that means they will be very accurate. Some of the models that show lower confidence, they may not be as accurate in the lower confidence, but maybe vice versa, like in the medium range of confidences, where they will be more accurate. So this is important in practice. That I want to show you something. Let's see. So let's come back to accuracy. And let me note here that yes, accuracy is a bad metric. It has lots of problems. And as a researcher, as a machine learning or data scientist, or a person solving problem using scientific method, you should know that it's a bad idea to use accuracy. But if your stakeholder, say, already has accuracy in all of their marketing material, and that's how they sell their product, that's how they will be convinced if you show them accuracy. You can't come to them with F1 score and you will spend a lot of time educating them. Use F1 score for yourself, deciding on which models to use, but come back to them with accuracy. So what we've seen with profit curve is something that can translate into this accuracy coverage curve. So this 100%. This line is coverage. It is the same, exactly the same as before, as with the profit curve. And let this be balanced accuracy, or any metric your stakeholder uses. And of course, you sort your samples by the score. So again, 1 or maximal possible, right? So it can't be higher. Imagine we have one classifier that is like that, another classifier that is like that, and yet another classifier that's like that. So the question is, which one is better? Which one is to prefer? One thing I want to stress out is when we take our whole test set and compute one single number, we are computing this number, the average performance over classifier. And so those are like really bad. This one, well, that couldn't be the case. Let's, I think this will be 0.5 line, then when it's easier to deal with for us. So this classifier will plummet at some point. Well, even 0.5 is not realistic, but stay with me. The point is that at some part, the classifier is just always wrong. It just stopped predicting and everything is wrong. Similar cutoff is for this blue classifier, similar for red. It happens somewhere, although it keeps trying up until here. Some of the predictions are correct, but for this green one, all of them are wrong after this certain point. So which one is better? First thing to think about is, what is your stakeholder requirement of permissible accuracy? And if this requirement is somewhere here, look what happens. This happened by accident, but anyways, this is the coverage at the requirement that I will get with the green classifier. And this is the coverage. And to compute this dot, we don't go from here, we go from this line, because on bulk, on half of the data, this classifier, the red classifier, will provide the required accuracy. The fact that it's very bad when it's highly confident doesn't mean that on average 50% of the population, if you choose an appropriate threshold for the red classifier, it's always about choosing the threshold as I described before. It will be good. So for the blue classifier, the coverage is even lower. So if this is the requirement, the orange line on the quality of your classifier, then you should select blue, and you don't care that your average performance on this test set is the lowest, because it can get highest degree of automation to your customer or your company. It will automate 70% or close to it of cases. and if you and be correct within the tolerance. On the other hand, if your threshold, if your requirement is higher, then potentially the blue classifier will become the best, if because it's very accurate, even though on a very small percentage, but still none of those classifiers give you that coverage. So you have to have all those things in mind when you're evaluating your classifier. Just blindly evaluating one number on the complete test set you'll throw away the baby with the water, basically, if you do that, because there is a lot of richness and possibilities there for you to solve the customer's problem, at least on to automate away large portion of their manual labor that they're currently doing.